Hello, everyone. We're 5 a.m. We are the design group in charge of designing a municipal HDPE recycling plant. I'm Joshua Reyes.
I'm Lindsay Carranza.
Anuja Oak.
Jolene Sharoma.
And I'm Vivian Tren.
So going into the agenda for today's presentation, we're going to start with our background and objectives, follow that with our process flow diagram and design, and then talk about our economic and environmental impacts, and finally end with our conclusions and future recommendations. So long story short, there is a major sustainability issue in America right now as recycling facilities in our country have not been able to keep pace with today's growing waste stream. Reinforcing a strong domestic recycling infrastructure is imperative in order to eliminate much of the waste going into landfills and cut down on the avalanche of new plastic being produced every year. High-density polyethylene, otherwise known as HDPE, and other plastics account for 12.8% of the volume of household solid waste generated in the US, with nearly 10 million metric tons of HDPE alone produced annually. Its high market volume and growing demand as plastic makes it a particularly profitable candidate for municipal recycling. In addition, products are ultimately cheaper to produce with recycled plastic rather than with virgin resin. These combined attributes make HDPE a promising material to be repurposed and sold to businesses. With this in mind, our ultimate objective was to confront America's recycling challenge by designing a facility based in Tucson, Arizona, that processes HDPE derived from municipal recycling programs into two distinct product streams. Our first stream will contain high-quality, food-grade clear pellets with 99.999% purity rates to be reused as packaging material for food and beverage companies, while our second stream will contain low-grade dyed flakes with 99% purity rates to be reused in construction material manufacturing. We have been able to closely collaborate with another senior design group from the chemical engineering department that specialized in sorting plastic materials to determine a lot of our inlet values into our plant. In addition, another senior design group focusing on manufacturing recycled plastic bricks for temporary disaster relief construction was identified as a major buyer of our low-grade product stream.
There is a process flow diagram that depicts the plant's continuous process that operates 24/7, 365 days a year. At the inlet of the plant, HDPE jugs are supplied to a bottle wash tank with hot water, sodium hydroxide caustic, and detergent. In this step, 99% of the contaminants in the jugs are removed. The jugs are next conveyed to the grinder, where the jugs are ground to 5 to 10 millimeter flakes. These flakes are then sent to a flotation tank to separate the HDPE from contaminants by density. At this point, the HDPE flakes have reached a purity that is satisfactory for the construction-grade recycled plastic bricks manufacturing. These flakes are sent to the sorter where they are optically sorted into two categories, dyed HDPE and clear HDPE. The dyed HDPE is sold to the brick manufacturers, while the clear HDPE must be further cleaned to reach food grade. The clear HDPE is sent to the flake wash, where they are then rinsed with hot water and detergent. The clear HDPE flakes undergo a final rinse with pure water to remove any residual detergent from the previous step. The final step in this process is to send the flakes to the extruder, where the flakes are molded into clear HDPE pellets that will be ready to be sold as the food grade product. This diagram also depicts the wastewater streams from the bottle wash grinder, flotation tank flake wash, and flake rinse, leading to an on-site wastewater treatment where approximately 65% of the treated water can be reused in the continuous process to allow for a reduction in water consumption. Since both hot and room temperature water are involved in this process, 2 heat exchangers have also been placed to reduce energy consumption. After many points in consideration, this design was determined to best meet our objectives.
Jumping off of the PFD, we actually made a 3D model of our recycling process plant in Minecraft, actually. So here we have our inlet of dyed HDPE and clear HDPE going to our bottle wash, where, as Vivian said, a lot of the solid contaminants and food grade stuff are removed, and with caustic and detergent. So here we have again our bottle wash, the wastewater stream coming off of it and to be treated to the wastewater plant later. Afterwards, it's sent to a grinder to be grinded down into flakes for easier processing downstream. In reality, these would come out as flakes, but right here, it's still just blocks. After the grinder, it's sent to a flotation tank for further cleaning. After the flotation tank, it's sent to a sorter where it's the di-HDP and clear HDP are separated into two streams. At this point, the di-HDP is done and is sent off as product, while the clear HDP is sent to a final washing step, flake wash and a flake rinse, and then finally an extruder where they are turned into pellets and sent off as food-grade HDPE pellets, clear, without any dye in them. So here those over there is our flake wash, and our flake rinse. And then lastly, our extruder. And that's our 3D model.
The total capital investment of the plant is around $2 million, with on-site wastewater treatment accounting for the largest portion of these costs. The annual costs are around $13 million, with feedstock costs accounting for a majority of these costs. Assuming it takes 3 years to construct the plant will be profitable just 1 year after construction ends if the output is sold at 50 cents per pound for pigmented HDPE flakes and 75 cents a pound for clear HDPE pellets. 12 years after construction begins, the plant will have a net present value of around $19 million. Although the plant has to bear additional capital costs for water and energy saving measures, the plant will still be profitable.
Many of our design decisions in the plant were directed towards environmental stewardship in order to justify the merit of recycling facility as an alternative to landfills. These decisions also provided long-term reductions in cost. For example, the on-site wastewater treatment facility prevents harmful materials such as caustic from escaping the plant and allowing potential contamination off-site. In addition, water reuse saves over 20,000 cubic meters yearly of water. The heat exchangers were added to reuse heating energy required to keep the wash water to 82 degrees Celsius. The addition of these saves over 700,000 kilowatt hours yearly. In addition, the decision to sell dyed HDPE rather than dispose of it also saves over 12,000 tons yearly of HDPE from landfills.
As mentioned by Vivian earlier, 65% of the reclaimed water is recycled back into our process's wash streams, with the remainder going into the public sewage system. We would recommend refining the efficiency and quality output of the on-site wastewater treatment facility to further increase the percentage of treated water that is able to be reused in our process. This will be dependent on how technologically advanced equipment applied is, but some manufacturers are claiming reuse capabilities as high as 99%. More research and upgraded equipment will need to be conducted in order to further reduce the cost and environmental impact of the proposed design overall. And we want to end with a list of our references as well as acknowledgements. Special thanks to Rodney Keith, our mentor, and Dr. Adriana Brush for putting up with us for a whole semester as we developed our design.